Of output op amp shown in figure is, okay, we have to find the gain, okay, that is V naught by Vi ratio. Okay, since it is 0 volts, what is the virtual ground voltage at this point? Is also 0. Apply nodal analysis at this input side. Okay, so this is 0 minus Vi by, how many nodes are there? There are two nodes. Okay, this voltage we already know is virtual ground voltage of 0 volts. Let us take this node voltage as V. Okay, now write the nodal equations at the input side. So this is 0 minus Vi by R plus 0 minus V by R is equal to 0. From this I can say that Vi is equal to minus plus V, okay, into minus 1. So this is Vi is equal to minus V. Okay, now what is the nodal equation at this node V? This is V minus 0 by R plus V by R plus V minus V naught by R is equal to 0. From this I can write it as V naught is equal to 3 times of V. So what is V? V is equal to minus times of Vi. So this is minus 3 times of Vi. So what is gain? V naught by Vi is equal to, gain is equal to minus 3. So that is option D is the correct answer. Minimum number of NOR gates used to implement XOR is. Since NOR and NAND are universal gates, you can implement using these gates to convert it to any other gate. Okay, that is XOR, XNOR, or you can say AND, or okay, anything else you can construct using universal gates called NOR and NAND. Now, how many number of gates are required? If you see the construction of NOR and NAND, let us take this as a two input gate. Okay, first these two are given to a NOR gate. Okay, now this is the construction for NOR gates to convert into XOR gate. Okay, at this point of time you will get XNOR output, but what is the question? We require XOR. So at this point of time we will get XOR outputs. So how many are required? 1, 2, 3, 4 and 5. So option B is the correct answer. If the question is the minimum number of NOT gates used to implement XNOR, so what is the answer? Number of gates required is only 4. Similarly, the minimum number of NAND gates used to implement XOR is 4, whereas minimum number of NAND gates used to implement XNOR is 5. Okay. So option B is the correct answer.
Which of them are true? SRAM is used in cache memory. As it is true because SRAM is fast compared to the DRAM. And how do we design of a single SRAM cell consists of 6 transistors? It is true. And DRAM cell consists of 1 transistor and 1 capacitor. It is also true. In DRAM, the stored charge in the capacitor can be maintained only for short duration of time, because in DRAM the the data is stored in the form of voltages, because in the capacitor, which will lose its charge as a function of time, hence we have to refresh it frequently. So all the statements are true, hence option C is correct. 085 microprocessor carry flag is affected by the following instruction. There are 4 instructions are given as the options. Increment is nothing but adding 1 to the LSB, so it's not going to affect the carry flag at all. Complement accumulator is also not going to affect the carry flag, as well as ending is also not going to affect the carry flag, because ending is nothing but a logical operation, it's not an arithmetic operation. So subtraction is the only instruction which will affect the carry flag, so option D is correct. Is equals to x of n into x of n minus 2, then the system is, here this system is time invariant as well as a not linear. So and we have to check for the stability condition. So if x of n is finite, the y of n is also going to be a finite. Hence it is option B is correct. Response of a system is given as, that is, y of n is equals to, for the impulse response for the system y of n is equals to maximum of x of n comma x of n minus 1 is. Here from the data itself, see, y of n is choosing the maximum of the given two signals. So it is a non-linear system. If it is a system is non-linear, we cannot describe it by its impulse response completely. So options are none of them, that is option D is correct. Which of these is the wrong statement? If delta x of t is convolved with the delta of t x of t itself, that is statement A is correct, true statement. Comes to, if x of t convolved with the shifted impulse, then the signal is also shifted by the same amount, and x of t minus lambda 1 convolved with del of t, the t minus lambda 1 is nothing but x of t minus lambda 1 minus lambda 2. So statement D is the only wrong statement, because all the three statements which E, B, C are correct. So option D is the false statement. Hence option D is the correct. Is not lie on the root locus of a system. See, the open loop transfer function is given as g of s h of s. If we plot root locus for the given open loop transfer function, the poles are located at 0, that is origin, -1, -3. Here the point on the real axis is going to be in the root locus. To the left of it, to the right of that particular point, the number of poles and zeros are going to be odd. Suppose if we look from here, this portion is going to be in the root locus, and this is going to be in the root locus. This portion is not going to be in the root locus, that is -1 to -3. So -1.5 is not going to be in the root locus. Hence option B is correct.
This table for k equal to, he has given a block diagram. Okay, in that diagram we have gain k. We have to find out when this gain k is stable. For what value of k it is going to be stable, the system. Okay, now what is the characteristic equation we have to find? From that we can analyze the root locus, or we can also find Routh-Hurwitz criteria. It is better to find Routh-Hurwitz criteria, it will be easy. Okay, now what is the total block transfer function? Total block transfer function, if you reduce this one, okay, we will get it as k by s square plus 0.1 ks plus k. This is the overall transfer function of this block diagram. Okay, now what is the characteristic equation here? S square plus 0.1 times of ks plus k equal to 0. So this is closed loop transfer function. Okay, now what is Routh-Hurwitz criteria? From Routh-Hurwitz criteria we can find this one as s square s power 1, this is s power 0. Alternate terms 1 and k, this is 0.1 k. So what is this one? This is equal to k. Okay, when the system is stable, when k is greater than 0, or you can say 0.1 k is greater than 0. Okay, or this is also, it is found as k is greater than 0. So only one condition it is there. When gain value is greater than 0, the system is stable. When gain value is equal to 0, then system is marginally stable. This one is stable. When gain value is less than 0, then this is unstable. Okay, these are the three conditions which is possible for the gain value of k. So answer option is A, since we have to find out the condition for stability. Okay.